progress.
No, don't mess with the thing. Just let's start and then we will utilize it.
Well, I hope it's being recorded. That it's being recorded. Well, let's start. It's a pleasure to introduce Eduardo Gonzalez from UMass, Boston. And he will start with the second part of the thoughts on shift operators in quantum homology. And this is the continuation. Eduardo?
Yeah, thank you very much. So I want to go back 10 minutes in the notation because where we can establish the existence of the shift operators on the Smith-Torres case, and I said that we are very interested in the more general case, and in particular we want to define an action of this nilpec algebras, so we'll get into that. So take a loop group G, your favorite loop group, connected, whatever works. But in this case, it's just going to be the Lie group. Take your maximal torus, take your Y of it, and then we're going to be denoting working with the character lattice. And so this is going to give, touching back to the previous talk, this is going to give the continuous symmetry. Okay, and then the vial is going to be the final type of symmetry, so the discrete symmetries in this particular case. And so the affine vial is exactly this semi-direct product with the co-character lattice with the vial. And I'm going to be working with this t-hat torus. And so remember that you don't have really shift operators without working with the t-hat enhanced t-hat operator. If you remove the extra S1, then you are essentially just working with the second action of this particular case. And so or the Seidel element. And so that's part of this, interesting in what I'm going to talk next. And so the field is just going to be the equivariant parameters, okay, with the t-hat torus, and then this is just essentially identified with the polynomials on the polynomials on the Lie algebra, the torus here. And it had to be a check. So I'm working with the big torus, this enhanced torus, big hat in the symmetric algebra that represents that. So and then the rotation of the loop. So there's one action on the loop group by rotations with the negative A, so the backwards type of rotation, at least for now. So as I was saying before, so there is a G hat and T hat action on the affine flag, which is defined as LG mod T. Okay, and you should be thinking about this affine flag as just as the kind of an analogous, an affine analogous of the usual flag. But anyway, so we defined a convolution product last time, and I just want to mention that it comes from the fact that you can. The actions are all twisted in this particular case. So there's this particular convolution product that we found yesterday. And I just want to mention that whenever you localize, right, so the cohomology, the equivariant cohomology of LG on T, if you tensor with a fraction field, then you can express that convolution product in a nicer way. So all the elements in this localized field is going to be in the localized ring is going to be F1 E W1 with the W1 tilde that represents it's just one of the generators in that ring N. And then the product is not direct. The W1 acts on the F2 coefficient that represents it. So there's a way of doing it explicitly and precisely. And I just wanted to remind you of that particular description of the problem. So then this new. So what I'm trying to do is to construct this action of the equivariant homology in the hat of LG mod T. So this is called the nilpec algebra on the quantum cohomology. The equivariant quantum homology of compact symplectic manifolds that we had yesterday. And so for that, we want to work universally. So the idea is to create a space that can parameterize all the possible Seidel spaces that you can have for each one of the loops that you get. Of course, you can construct this. This is going to be a non-finite type of business, right? So you are going to take LG, you cross it with N, and then you place a copy of the disk in one side. So that's your first piece. You do the same thing with a copy of another disk, which have one of the infinity, and then I do it through the particular relation that is explicit in this way. So the relation is you take an element in LG and then you glue along the boundary by the action of the loop that you have. And so it's exactly the same relation on the boundary that you had in the usual Seidel space. And of course, for each one of the fixed elements that you have in LG, that will give you Seidel space that we have to find. So then we're in this massive parameter space that we have. So we call that the universal space. This construction, by the way, is not due to explicitly. There's this guy, Sasha Savalia, in Coulomb, as a matter of fact, he was a student in computer myself that had this idea first. So he worked, he didn't have this particular application in mind, but certainly he worked with this before. So just to clarify again, so every single time that you work with LT, you have not only a T hat action, you have a T hat times T action. And so I'm going to use that to define a T hat times T action in this universal space. And so the action is defined there. So it's essentially you take the tau is going to be a time parameter, so it's like being in S1. The G and the H that appear in there are elements in the T.
Is this universal for what, or is just a name?
I'm calling it universal because of parameterizing all possible Seidel spaces that you can have. So of course, because you're doing it over T. Remember that if I give you a loop of Hamiltonian automorphisms in the symplectic manifold, you can always construct this Seidel space in it. So now I'm doing it as a whole family, and this is an actual space that you can construct with the same type of gluing Plotchin relation. It's just infinite time.
Is this a universal family of Seidel spaces from somewhere, or?
Yeah, well, not necessarily. So for each, so you have to be careful. So for each gamma, right, you get a Seidel space, but you have like copies of P1 for each one of the.
Yeah, but I mean, you could think of U as a universal family of Seidel spaces, the universal family over a modular space of Seidel spaces. In this case, it would be something hard.
Yeah, I haven't done. I don't know exactly where we're going. No, so in this case, it's just a geometric construction of that, but not universal in that way. Probably we can probably design it that way as well. Yeah. But anyway, so in this case, you have this T hat times T action. So remember the tau that person it comes from the S1, and then you have two toruses, tori. And then the action is what's given as I am describing in there. The action is defined in a way that whenever you glue the two chunks of this universal space, then it's compatible, and then you just descend. It descends properly to the universal space. The target, so we want to do the same exact construction that we did for the Seidel action, just in this case, we're going to focus on a particular target space, which is U mod T. With U mod T, the fibers are going to be a tiny bit easier to handle. Those are the ones that we want to think about. And the T is the quotient by the second torus that appears in there. So that I have the T hat action on the whole universe, the U mod T space. So with those conditions, then there are two special fibers. The fiber at 0 and the fiber at infinity. Now remember, this is a family of P1s that we have. So 0 and infinity should be understood as this parameterized section of 0 there's section at infinity. But so this section at 0, I'm using the language, is going to be isomorphic, identified with the twisted space LG cross M mod T. So this is the twisted product construction, and the fiber at infinity is the twisted one. So the action on M is the action of T on M is trivial in that case. So then the diagram for the Seidel space in this case, in this universal, version of it as a shift operator is given by considering those two fibers and then counting sections that don't connect cycles from one side of that fiber to the other one. And so we use a modularized space to parameterize sections in a particular way that we'll probably describe it in a second. But this is the general idea. So once you have this universal shift operator that connects these two different fibers, then what we do in order to get the Seidel action or the shift action, the universal shift action, is the is the composition of that universal shift operator that appears above, from the twisted to the untwisted, and then apply the topological map that I described yesterday for any space that has a t-hat action. So remember, for any t-hat space that you can have, there is always a map topologically constructed from the equivariant cohomology of L, G mod T to the twisted space. So this is the twisted product LG cross M mod T. And so this is what we do. We construct this map first, this universal shape of correspondence, if you want to call it, and then we consider the topological map, then this universal shift, and then I project to M. And so that composition is essentially what gives me the universal shift operator. Don't you see a lot of problems with that construction? So the problem is that
suppose that you had a section of the frequencies, why you were just wondering.
What do you mean?
Well, you can pull it or push to one side or the other vibration.
Yeah, exactly. That's more or less what you're doing with the push. But very good observation. So I want to do that. So the things that the pull and the push forward should be done through these moduli of sections. And so we have to make sure that those things are well behaved, right? So that's the first challenge. So how do you do the pull-push construction, which is, you're absolutely right, it's just a correspondence. And so we are doing that over the modularized space of sections. And so the challenge is that to approximate everything. So the first one is that you are working on infinite time. And so you want to bring back everything into something that we can control. And because we want to define something on these maps at the level of homology, then we want to work with cycles. And in a way that we can control it. And so this is the next part that I'm addressing here. So there are many people that have worked with these parameterized finite dimensional approximations versions of doing these correspondences with the sections and modularized spaces. The one that we're going to use is I already mentioned by Savaliev, but also by Michael Hutchins has done this in for flow and homology and so on. It's called construction in families. And so for that, the first thing that we're going to do is again do finite dimensional approximations to the Borel spaces that we're working with. And so for any cycle that you have, or for any map B that goes from a certain manifold B, this is a finite dimensional manifold, the base that I have there. So for every map that goes from that B into the Borel space of LG, remember the Borel space that I am taking is with respect to the t-hat action on LG. And so I'm going to look at the universal construction of this, and then that defines a Y version, like just if I look at the Cartesian diagram that this defines. And so what this is really doing is constructing a new bundle, which I'm calling PF, that is Cartesian, it's a Cartesian product of the U Borel to the L Borel through them. So this is how it goes. And there's a more geometric description of this EF is essentially this Seidel space of this universal space, but now of finite type, where instead of taking the whole of LG, you are taking this approximation Y to that thing. Okay. So this is where you do the geometry. So you eventually have to do the geometry in these things. And then the definition, as you were saying, so now it's a pull-push construction. So the modularized spaces that we're going to be working on is every single time that you take a cycle given by that F from B into the Borel construction of LG, as well type of approximation. So you look at the moduli space of sections on that new space, and that's going to be very well defined as finite dimensional, as a matter of fact. And you have to make the choices of a particular, almost complex structure, particular symplectic form on that space, and then everything now makes sense as before. So the work is really just trying to do everything very carefully, so that the symplectic geometry that you knew before can be applied in this case that we have. And then you do the full push. So then that map CF, which is the correspondence that we wanted to talk about, essentially just given by pulling back a representative of the cycle. So if, let's say, your class was X, you want to apply this map to, then you're represented by a cycle. You take the final product with the moduli space that I have through the evaluation F0, then I do the push forwards with respect to the evaluation at infinity, and that lands in the fiber that is untwisted. So remember, now I changed the thing. So I'm certain from the twisted version of it to the untwisted one, so that just because I want to use this topological maps that I constructed yesterday. So that's essentially what you do, and then more formally over here, really you have to be very careful. If you just work with smooth loops, then you don't have really nice algebraic cycles approximating LG. You cannot do beautiful geometry, so you have to work with polynomial approximations. So it's very well known. It's in the book of firstly, I think that Seidel, that this is a homology equivalence to the continuous and the smooth spaces. And so I take that CW approximation through the composition that we described yesterday, and then I can define the cohomology, this cohomology that I'm presenting here as limit of the Borels. So when of Borel approximations, and once you have that, then each one of those pieces. So if I do the construction that I did above, and I do this approximation of the
in the Bruhat cells.
It's exactly so the thing that the Bruhat cells have. So I'm thinking in only considering the polynomial groups, not the algebraic ones. I mean, because otherwise it gets you cannot do geometry in these things. But anyway, at the end of the day, each one of the pieces is acting on the quantum cohomology, the equivariant homology of n, and then you can just take the limit of that action. That's essentially how it goes. So the construction is entirely tricky, but it's all due to using approximations and so on. The properties that we have is just as you can expect. If you take one as the standard class, that just returns identity, okay, and then it's linear with respect to the base to the equivalent ring. So if you apply the shift operator, this universal shift operator beta times alpha, then that gives you beta times the shift operator, so that's not a problem. And so this construction gives you a nice, so essentially the action that I was thinking of, at least in for the torus T hat that I have. And so when you want to prove the module property, so the module properties, of course, you want to see that the map is that gives a module structure of the quantum cohomology over the ring of the homology of the affine flag, then it gets a little bit tricky. So for G, if G were just a billion, then there is no problem. You can if it were a torus, then it follows from work of Unitani, which we already discussed yesterday. So you can just apply the same ideas and everything is perfectly fine. So what we're going to do in order to prove this module property, this is a beautiful idea done Pomerleano actually. So you pass through you localize. So I already mentioned that you can use localization whenever you multiply by the localized field, right? So you just take that, so I'm going to work at that level. And so then it's enough to prove the modular structure at the level of fixed points. So localization means that I can just consider the fixed points MT for M, okay, in M. And in that case, I want to show that the map that I have in this case, so I'm going to call for each fixed point component, if you want, of MT, you get an action that comes back to it. Or you can just think there's
How do you reconstruct the whole modular? How do you reconstruct the whole action?
the whole action is because by localization, so you essentially can the whole ring is given by localization. Because I remember tensoring with the localized field of revisions, the field of fraction. So I should be putting log in that, but notation will get really tricky. But anyway, so in that case, you have a map that goes from the fixed points of M into itself, and then you have the this action. By the way, instead of F, it should be like the union of F's in that. Very much. So the modular property will be equivalent in this case as every single time that you compose the two Seidel maps coming from one parameter subgroup times W1, which is an unlimited divide. So those are two elements in the affine bias. So if you multiply those two, then that should correspond to the shift operator of the product of the two generators that you have. So this is actually what we want to do. And I already mentioned, so if you were working only with the abelian case, that means with the torus, this is already done. You already know it. So there is nothing to be done in that case. So for co-characters, for one parameter family for loops in the torus, then this is taken care of. The problem is if you have this action of the divide loop, and then that's when things get very tricky. So the claim is that the action of the divide loop also acts on the manifold, because remember that I already established the action of LG, the homology of LG T in general, so then it's acting in there. But then in order to get the relation that I want, what you do is just artificially do this, the trick that I learned from Dan, which is, you just introduce, if you want to see what this is, you have sigma 1 W1 as sigma 2 W2, and then you just multiply by this guy in here, right? So the W1 minus 1 in that. So you just introduce it. This should be a sigma 1. And then you take the first operation. This is only the map that you get from the phi element. And then that gives you this, conjugate one parameter subgroup. But the W is in the normalizer of because it's in the vial, so it will preserve the one parameter subgroup in T. It keeps it in T. And so then you can apply the rule that appears in there. So there is a module on one parameter subgroups in the torus, in the co-characters, and then you just use the module structure. The point is not working, but so that last line is exactly what I'm doing. I'm using the module structure on the co-characters, and then it follows from there. So the moral of the story is that, very similar to what happens whenever you want to compute equivariant homology of, with respect to the group G, you look into the invariance of the equivariant homology of T, then this is the same situation here for the operation. And that's what happens. And so we can also prove the conjugation, not conjugation, the commutation with the quantum connection. In this particular case, because I think that you probably forgot already, so I am only working on the special case where the manifold is monotone, so it only really is interesting to look into the C1 direction in this case. So the C1 is the equivariant Chern class of M that you have, and so we can prove the same result just by doing it on the torus case first and then passing it through the divided variance, and so it commits with the connection. No, bless you. So some idea. So now I'm going to start doing some actual motivations of where all of this came and why we wanted to do it. So this is the Lagrangian description of quantum cohomology. So, let me see. So the loop group of G, the base loop group is just given by LG mod G. What you are seeing G as the constant loops inside LG, right? So the convolution gives you a product also on the equivariant homology of the loop group G, the base loop group, with the equivariant homology with respect to G hat. What you are seeing that, so the description that Bezout, Karpov, Finkenberg, and Merkovich gave is that you can see that algebra above embedded in the Nilhecke algebra, the equivariant homology of the partial variety with respect to T hat as a spherical subalgebra with respect to the symmetrizer. Okay, and so that gives you a family of essentially. So this convolution product is some sort of a family over U, where U is this S1 equivariant parameter. And when U is equal to 0, then that gives you the contrarian ring. So it corresponds to the contrarian ring. So you can think of this equivariant homology with respect to the G hat of the base loop group as a flat formation of the contrarian ring. Okay, so that's the first thing. So if you take the spectrum of over here, the spectrum do correspond not. This is not a mistake. There is no G hat in that. So you are now ignoring the G hat. So the spectrum of HG, loop G is a smooth holomorphic symplectic variety. The equivariant homology of M with respect to T is a module over that particular ring, and it's preserving. And again, I put the hat in there. You should remove the hat in the part books in this one. So it preserves the Weyl variance. So you're again taking the Weyl variance of the equivariant homology, the quantum equivariant homology with respect to T. You take the Weyl variance that gives you the equivariant homology with respect to G, and it's not that difficult to see the support. So that you can see the quantum homology now as a sheet on the spec of HG loop G, and so the support is actually isotropic and of maximum dimension, and so therefore it's Lagrangian. This spectrum in here, the spectrum of that particular ring with the contrarian ring is called the Coulomb branch proof, the pure Coulomb branch. I will probably talk in a second about that. So the example that you should keep in mind is again the toric case, the toric variety case. So if you have a toric variety just presented as a quotient like that, so the space that I just described, the spectrum of that ring, right, is just given as a spectrum of the polynomial ring U1 to UN, and then you take the Z1 plus or minus ones. The Z to correspond to the Seidel coordinates, so the torus coordinates. The UIs are the equivariant parameters. And with respect to that symplectic form that appears in them, which is logarithmic in the Z variables, then you get the following description of the quantum homology. So you look at the equivariant Horibach potential that I defined yesterday, so which corresponds just to the sum of the Horibach potential, the classic Horibach potential in the usual case, plus this equivariant addition, which is UI log Zi. And so the Jacobian ring of that superpotential, right, corresponds to those relations that appear in there, and this is inside the spectrum of that. So it just happens that I is a Lagrangian variety of the spectrum. And so this is exactly what we are trying to say here in the Lagrangian description. But anyway, so this is linked to what the original motivation of this work was about. So the physics motivation is that even a group acting for Cantillon representation, there's always many moduli spaces that you can associate to them. Amongst one of them is what is called Coulomb branch, and of course, it's very difficult to define what the Coulomb branch is in general, but Bremerman Wickelberg and Nakajima came up with a construction for the particular case when this quaternion representation is given by just a sum of B and its dual for the complex representation, for a complex representation, complex unitary representation of D. And so in that case, they gave this model, this construction of the Coulomb branch as the spectrum of a particular algebra, which is a Poisson algebra. And in the case when E is equal to 0, it's exactly the perfect range that we're looking in there. So then that's a connection with these Coulomb branches. And in general, so what we discussed today so far, and what we have covered right now, is essentially that case for M being, an action of this, so the Seidel, the shift action, the shift operator of the quantum cohomology is essentially this pure Coulomb branch version of it. Okay, so what we wanted to extend now to the case is trying to use this construction to tackle the case, and this is through suggestions of Konstantin Telemann, of course, and he has written so many really beautiful papers on the subject about the construction of the Coulomb branch in this particular case, the Nakajima, Bergerman, and Wickelberg case. For that, you need symplectic homology, but symplectic homology, is not very common for people to know. So I'm just going to do a quick review of what symplectic homology is. So everybody knows Hamiltonian fluid homology. So I'm going to start with that. So consider the Hamiltonian family that is time dependent. So this is a family of functions that is in my compact, a closed symplectic manifold of your choice. And then you consider the equation given by these loops of the Hamiltonian flow that the family gives. And so those solutions to that equation that appear in there are critical points of the action functional. So this is the action functional. This is taking values in contractible loops of M. So I know that I've been using loops in G, but these are loops in M. And contractible means that you can cap them, and you can cap them through a disk. So this is what we're doing here. So the action functional is just the integral of the full backward maps that go from the disk to M, of omega minus the integral of the Hamiltonian in the solution that you have. So fluid theory can be understood as the most theory of that action functional. And that's, again, the problem is that you are working on infinite dimensions, and so trying to make it correct is a little problematic. But anyway, so through choices, and in particular the choice that you make is of a family of almost complex structures, then the Hamiltonian, the flow, the Morse flow of the action defined by the action functional is just given by this fluid J-homomorphic equation, which is perturbed by the gradient of the Hamiltonian functions. So that's called the perturbed J-homomorphic equation. And you look at solutions of this. So this is, a PTE. You look at solutions. But structural solutions, they are going to be cylinders. In general, you need to compactify the moduli space, just as we do for any type of moduli curves. And I'm going to avoid putting the person here. So for that, I again use the monotone case, which is going to get rid of all the bubbles that appear in there. So I form a chain complex, which is called the fluid chain complex, by taking all the one periodic orbits of that I get of a certain index. So this is called the Coulomb index, and then I look at the differential that will count all the cylinders that appear in there, where the difference in with the difference of the index is going to be 1. Okay, of the moduli space. But anyway, so the theorem, which is of course a famous theorem of Floyd, is that this defines a differential from the Yucatek homology of this complex that gives you the fluid homology of the family of Hamiltonians that you had before. So it just so happens that, in the compact case, if you have two different families, Hamiltonians, or families of data that you have in order to construct the Fluid theory, it doesn't really matter. You can always find a homotopy that brings one to the other, and you can construct what they are called continuation maps from one, family to the other, one Fluid homology to the other. And it just happens. This can be done at the level, whatever level we want, and then so that there is this map is called a continuation map. And so in particular, in the case when you take Hamiltonian that is time independent, it reduces just to the Morse homology of M, and everybody knows that corresponds to the singular homology, with appropriate coefficients, and then you get the quantum homology, because the pair product in Fluid theory corresponds to the quantum product, and so you have this equality. So then, because quantum homology corresponds to this Fluid theory, then you have the action that we had before. Of course, this is nothing new. This was the original paper by Seidel. Actually, he mentioned that and that. So the problem that we have is that whenever we want to work with things that are not compact, that theorem doesn't apply. So in reality, there is no Seidel action in Fluid homology, but let me explain in what cases that happens. So if you focus on what they are called ubial domains, so that means that you have a particular one form that makes the, so you are working on a convex on a manifold M that has boundary now, and then you have a one form that satisfies that essentially the boundary is contact type. Then in that case you can construct Fluid theories with particular type of Hamiltonians. So let me explain that. So the Fluid data that you need in order to construct a Fluid theory from those type of domains, or ubial domains. Also, you can do it with things that are convex boundaries. So they are essentially ubial domains that, like ubial domains, but only at the level of the boundary. So this form exists only at the level of the boundary, not on the whole manifold. But anyway, so the type of Hamiltonian functions that we're going to work with are called cylindrical. That means that they have a slope at infinity. So that means that you can always represent them in that particular end. So remember, I'm attaching some sort of cylinder continuation at my manifold. And so I want that on that cylinder, so the cylinder, I'm calling it with coordinates R and Y. So the R is the length of the cylinder, and then the Y is going to be an element in the boundary of M. So in that case, I want the Hamiltonian to be R times the slope. So that's a function that goes from S1 times boundary to the reals, plus a function that only depends on the circle. Okay. And then what happens is that this slope, you also it's going to be cylindrical if this slope is invariant in the Bragg field. I'm not going to get into details of that. There's a particular vector field and then S1 is invariant to that. And so the definition is that you say that two Hamiltonians are going to be compared, or one is smaller than the other, if the slopes are smaller. And in that way, right, whenever you want to do the Fluid equation for the Hamiltonians, and then they are comparable. So you can actually get continuation maps in that way. So the construction of continuation maps holds because the maximal principal contribution to the equations that are involved actually the conditions are satisfied, and then you can have a map like that. And so the symplectic homology of the manifold M that you have with the boundary is actually defined as a limit of all those Fluid homologies, the direction with respect to the slope, and that gives you a good definition. So it just so happens, as I was mentioning before, that you don't have a Seidel action in general, because the Seidel action increases you don't have a Seidel action in the Fluid part, because the Seidel action increases the slope in some sense. In some cases you don't even can compare them, but even in the cases where you can increase it, and so the action is only at the level of symplectic homology, and then you can do the same thing that we had before. Okay, for the symplectic homology, I'm not going to go into details, but you can assume, you know, or what I'm trying to say is that you can just do the same thing as before, you know, to do the construction of the action. And so again, as I was saying before, the problem really lies in the fact that you know, if you take a look in G, I'm assuming the action is Hamiltonian, then it will increase the slope. Anyway, so the properties is that if you have if you evaluate that the identity, right? So remember that I am considering now the identity in this case is the element in the symplectic homology. So that gives you just a map that goes from the equivariant, the T equivariant homology of the loop group into the symplectic homology of that. And then you also get a map that goes, you know, just as before by taking the invariance. Then you will get a map that goes from the Coulomb, the pure Coulomb algebra, Coulomb branch algebra into the symplectic homology of M hat, the equivariant. And so we have a diagram like this, and this is only the case. So remember that for the Coulomb branch, you wanted to consider representations that are unitary, complex representations that are unitary. And E was given by V plus V dual. And so this diagram that I present here, so the claims that, you know, there's a commutative diagram that, you know, sees, I am assuming that this map that I'm calling A, which is called the acceleration map of Viterbo, so that's injected. So that gives you a way of recovering the, this at the level of families. I'm not going to be very precise, but the point that I want to make is that this gives you a way of recovering the non-pure Coulomb branch using symplectic homology. And this is, you know, I am extending the action with the S1 action and so on. But, you know, I think I will probably mention that, you know, there's still it has been submitted here back. The idea is to extend the whole story for G hat, at least in the symplectic homology case, maybe trying to clarify a tiny bit more of this relation in that case. And then Coulomb branches also exist coming from Hager. And so that would be an interesting project. Probably it will take another so many years to finish the project in K-theory, but you have to go one dimension higher. So whenever you work with K-theory, you're one dimension in the Coulomb branch. So you're working with higher dimensional mirror symmetry in that case. But I think the amount of time, I mean, if you have more questions, I can explain